Thank you. Hi, everyone. So a few years ago, our colleagues Lee Campbell and Matt Barrett were on stage here talking about reactive user interface. Today, we're not going to be talking about UIs. We're going to be talking about the real-time services which sit behind those user interfaces. So as you can see there, this is a typical screen of a trading system. And those systems have the specificity that the products you are trading on those platforms have prices which are constantly changing. So those UIs are constantly ticking. And you can't use the typical request-response paradigm to build those systems. So our UIs, our backends are very much message-driven. So they send message from the backend to the UI, from the UI to the backend. And server-side, we have multiple services, multiple components, which are passing message between each other. So if we look at the core attributes of the systems we are building. So one, we already said, our system, our services are message-driven. Typically, our services need to be very responsive. It's not rare to have response time requirements below the millisecond. In some scenarios, it's even at the microsecond level. In terms of resilience, the traders using those platforms are, at the click of a button, transacting multi-million trades. So those systems need to be very resilient. We don't want to lose the trade or the order of a customer. And also something quite which we have quite often in those systems, we have to deal with quite complex business logic. So we have complex products and complex workflows to orchestrate between traders or between a trader and a machine. So what we typically see when we build those systems is that we end up building services which are highly multi-threaded. And when you combine multi-threading and a complex domain, complex business logic, generally you end up with a service which is quite hard to reason about. So it becomes hard for the people who built it initially, and it's even harder for the people who are going to join the team down the line. Another thing is that those systems tend to be very difficult to debug. Like when you receive a call at 2 a.m., you are connecting to the production servers, looking at a spaghetti of logs published by multiple threads, and you are having a hard time figuring out what is going on into this system. And it's generally quite difficult. You can have some like nasty concurrency issues, and those bugs are difficult to reproduce. A few years ago, something really interesting happened, at least interesting for us. So Dave Farley, who is sitting just there, and Martin Thompson talked about the architecture of the trading systems they were developing. So they were building a very high-performance exchange, financial exchange, and they talked about their architecture, but more than giving away the architecture, I think what they gave away at the time was really a blueprint to build those style of services. And I think something that I find really interesting in this architecture is how they achieved to draw a very clear line and achieve a very clean separation of concern between the business logic, which run on a single thread on this architecture. So you have a clean, stateful model in memory, which gets mutated by a single thread. And you have all the technical aspects which are managed completely separately by your technical infrastructure. And this allows us to basically not have to worry about the technical aspect, but we can focus on the business logic and build a very clean model based on our business requirements. And as we will see, those systems are also awesome from a debuggability perspective. It's very, very easy to reproduce a problem with this architecture. So we did not, so we are a consultancy. We did not start a project for a client by implementing the full, complete architecture that LMAX was proposing. What we did instead is basically we picked up some ideas one by one on different projects. And in this talk, we are going to run you through this journey. And so in the first stage, basically what we did is we tried to get this simple single-threaded model. We also got the possibility to easily debug our system. Then in a second stage, we started looking at clustering those services. So basically to be able to achieve a transparent failover of our services, and also being able to replicate consistently our state between the different nodes in our service. And finally, in the last stage, basically, we managed to get those clusters to be kind of self-sufficient in terms of state. They did not have to store their state in a database. They can basically achieve the durability of their state by themselves. So James is going to run us through the first stage.
Thanks, Olivier. So the first problem that LMAX kind of, that I want to draw attention to is the simplicity of the model that you end up having when you use this architecture. So what we get with the kind of deterministic execution in a distributed event system is a kind of a very kind of nice way of looking at the problem and a nice way to model. So I'll start to talk about what determinism is. So it's a standard computer science term. You're probably all familiar with it, but if you aren't, here's what it is. So you have an initial state and you have a command. You apply that command to the state, and you should always end up in the same state and produce exactly the same side effects. So there are a couple of things that we need in order to have determinism in a kind of distributed event-driven system. The first one is a log. So show of hands, who's using event sourcing in their architectures? Okay, so a few of you. So for the rest of you, the log is an immutable sequence of records that's totally ordered by time. So it's a great way of representing a sequence of commands that's coming into your system, and it's a very efficient data structure to use in memory and to write on disk, because you're always writing at the end. You don't have to do any random seek. You start at the beginning, you read through the whole thing, and you write at the end. So the other thing that we need for deterministic logic in a distributed system is a single-threaded log consumer. So we've got, imagine the scene, in our logical architecture, we've got a log. We've got multiple clients and multiple threads passing messages onto the log. These are being sequenced, written to disk, and on the other side of that, we've got a single consumer, which is our model, which is working in a kind of while loop, pick a command off the log, apply the state, the command to your state in memory, and continue like that. So this kind of single-threaded logic, typically the question we get is, isn't that super slow? Shouldn't we be using all the cores these days? We've reached a kind of a limit in the speed of processors now, so shouldn't we be using all the cores? So the answer to that question is no. I mean, typically, if you're doing not very kind of stupid stuff in your code, you can achieve kind of 10,000 operations per second, which is kind of fairly typical in a click type architecture. If you need kind of more performance than that, you can increase the order of magnitude just by kind of profiling your code. If you need to get kind of really fast, if you need millions of messages per second, you need to start looking at the data structures you're using. You can't use the standard kind of list implementation in your class library. You need to start kind of optimizing for the problem you have. So you typically want to be using algorithms to manipulate your collections, which are constant time or log n time. And when you're kind of dealing with this model that is affecting your state in memory, typically what happens is that kind of act of decoding the command off the wire typically becomes your bottleneck. So you need to really think about how you're getting the command off the wire. So if you were to use standard mechanism is to deserialize the object, use some kind of protobuf type serialization, well, that creates an object every time you do it. So instead of that, if you can use libraries like SBE, which allow you to read straight from the network, they allow you to read the relevant fields without performing any copy or any allocation, you can typically kind of reduce the amount of time spent decoding and encoding your messages. So, I mean, that's great. The other benefit of not allocating in your code is you don't put pressure on your heap. So if you garbage collect halfway through through processing a command, you typically get an unpredictable latency in your system. So that's another benefit of not allocating in your code. So with determinism, there was the first thing we came across was handling time. You need to be able to get all of the inputs to your service from the log. So you can't use your standard system time when you're processing, if you need it on a transaction to be able to say when this transaction happened, or if you need it to schedule events, for instance, you need that input to come from a log. So what we do is simply, when the client sends a command, at the point that it's persisted to the log, we take the timestamp and add that to the command. So at that point, when the service needs time for any reason, it can use the timestamp straight from that message, and we're all good. So we can replay. So anytime you replay the log, no matter what time of day it is, it always ends in the same state, and your last update times are all correct. So we talked about easy debugging. So Olivier was talking about kind of a multi-threaded system. You've got kind of difficult to read logs. You get a call at 3 a.m. and you want to kind of reproduce the situation. So with this architecture, because we've got a log and a deterministic model, we can just go to the production server, download the log onto our local environment. We also go to GitHub or wherever your version control is. We grab the same version of the model, compile it. We're in your dev environment. All we then do is just replay the log through the model. We get to exactly the same stage as where we were bugging up before. So let's kind of have a look at what's going on in this service. What does it look like? So if we take a look at the model, we've got, the first thing I want to point out is that we've got a kind of very distinct line between where our infrastructure is and where our model is. So the infrastructure is taking care of all of the network I/O for us. It's taking care of sequencing the commands from multiple clients coming over the wire. It's journaling journaling those messages to disk, and then it's passing messages over to the model. So it's a really clean split. It allows us to kind of it gives us a very nice bubble in which we can kind of model our business problems. So just taking a step through, if we get a message off the wire, that's taken in the inbound I/O, so the message is obviously coming in off the wire in bytes. So that's passed over to the sequencer, which is kind of typically taking multiple consumers and establishing a total order of the messages that we're consuming. So once we've got a single sequence of messages, that's passed over to the journaler, and we write it down to disk. So then it's passed over to the model. So it's worth saying that we're still dealing in bytes here. The infrastructure is not concerned with the semantics of the message. We're dealing with kind of bytes. So when it's passed over to the model, that's where we decode these bytes and turn them into a kind of usable command. So in this instance, we've got a deposit command, and we've got an amount of 100 and a count of A. So we're taking that command, applying it to the model. So this is all still being done in memory. At that stage, we can acknowledge the command. So we have an ACK that then gets encoded, sent over the wire back to the client. So if we zoom in, we're hiding our infrastructure, that's down at the bottom still, but if we zoom in on the model now. So I talked about the bubble earlier. This is because we're hiding all of the network, all of the kind of complexities of the threading and the asynchrony. We've got this really simple bubble in which we can kind of model our business problem. So I mean, the model's not important, but what we can apply now is kind of very practical DDD type principles. So we can think about the relationships, but we can think about our entities, we can think about the relationships between them. We can think about the appropriate data structures for modeling those relationships. We can think about the performance of those data structures for modeling those relationships. So, I mean, it really allows us, so this context of a deterministic model with a single thread where we're dealing completely in memory allows us to really kind of focus on the business problems at hand, and we think it's a really powerful model.
Thank you, James. So that was the first stage. So during this project, basically what we managed to achieve is we had this simple model decoupled completely from this technical infrastructure sitting below. And as James pointed out, we are able to very easily debug our system. So we can download the log, replay, and get exactly in the same state where we had our production issue. In that project, clearly, so far we have been talking about a single instance of our service. In reality, in production, you need to have multiple instances for fault tolerance reason. So in that specific project, we had use case and scenarios where we had to synchronize through a database. So I'm going to give a bit more detail about that use case. So for that platform, traders, when they try to transact, the platform would check that they have enough credits. So we need to check that this trader is able to perform that trade and has enough credit in his bucket. The problem is when we do that, we can have multiple traders from the same client connected to different servers. So we run in the typical situation where we have a model at the top and a model at the bottom, where they have a current different view of the state, they are not consistent, and the only place where we can synchronize is through the database. Also in our use case, this credit logic was very complex. It was like a full library on its own, and that's not something we were able to perform directly on the database. So what we ended up having to do is basically when we receive a transaction request from a client, we'd have to go to the database, load the credit information, perform the credit computation, and then try to commit back the credit to the database. The problem is, in the meantime, while that was happening, another trader connected on the other node could have performed a transaction which impacted the credit. So basically, we need to not commit the transaction, roll back, and rerun the full process. So that's quite a complex dance to orchestrate, and we will see how, in the next stage, we have been able to alleviate that problem. So now we're going to talk about fault tolerance and state replication. So this is the architecture we are going to have in this second phase. So instead of being synchronizing through a database, now we are able to replicate state between multiple instances of our service, of our model. And that gives us fault tolerance. So if we lose one of those servers, we are able to carry on with the remaining instances. And also what we will see is that we are able to replicate state completely consistently between the nodes. So James is going to run us through this second phase.
So what kind of failures do we need to deal with when we're talking about fault tolerance? So we got a case where a server fails. That's a fairly obvious one. But we've also got cases where the network fails. So if we've got two nodes that don't know about each other, we want to make sure that they are not answering they don't have different answers to the same questions. So this is a distributed consensus problem. And luckily for us, it's been in universities for decades. I think the first paper was from 1978. It's about view-stamped replication. So we're going to use one that's a bit newer than that. It's from 2013. A guy from Stanford in his PhD paper, Diego Ongaro, he introduced this problem, or he introduced this solution called Raft, which is typically the issues with previous consensus algorithms were they're tricky to understand. So the primary goal of Raft is to be super easy to understand. So typically in Raft, we're dealing with 3 nodes, or it could be 5 nodes. So in a 3-node cluster, we can tolerate the failure of 1 node. In 5-node cluster, we can tolerate the failure of 2 nodes. With network partitions, it's the same. We've got 3 nodes, and you can tolerate the failure of the partition of 1. And if you've got 5 nodes, you can tolerate the partition of 2.
Yeah, just worth pointing out, basically you always need to have a majority of nodes available. So you can create a 7-node cluster or even more, but at each point in time you need to have more than half of the nodes which are able to connect and talk to each other for the cluster to remain available.
So the first thing we need in Raft is a leader. So when we start our nodes in the cluster, we start with 3 followers. One of them will, after a random period, realize we don't have a leader. It will nominate itself as a candidate. It will send out kind of a request for vote to the other nodes, and once it's received a majority of votes from the other nodes, it can become a leader. So at that point, we've got clients on the other end trying to find a leader. So they will have a list of the nodes in the cluster, and they'll be randomly trying each one. If they connect to a follower, the follower will redirect it to the leader, and if they connect to the leader, then it's all good. They can start sending commands. So the client sends a deposit command, same example as earlier. The leader will persist that command to its disk, to its log. It will then notify the followers about that command, and they'll do the same. So they'll persist that command to their logs and will acknowledge that back to the leader. So the leader, once it receives a kind of a majority of messages back from the followers, will commit that command, and it will apply, and it will free the business logic to apply that command to its state. And simultaneously, it will be sending a message to the followers to tell them to do the same. So at that point, we can acknowledge that command and send a response back to the client to say, right, that's done. So, and it's worth pointing out that the followers, because they're in exactly the same state, they're doing exactly the same thing. But because they're not connected to the client, those are just getting dropped on the floor. So it's probably worth talking a bit about failure scenarios when we're talking about fault tolerance. So say that leader fails, what happens? Well, we've got two followers, and after another kind of random interval, one of the followers will declare itself candidate. Because there are still two nodes in the cluster and it can achieve a majority, it will become a leader. So the client will try and reconnect in the same way as it did before. It will be trying to connect to random nodes, and once it finds one that's active, it will be able to find out where the leader is. So at this point, the client's connected to a node that was in exactly the same state as the previous leader it was connected to. So in this way, we're able to achieve a level of fault tolerance that, where we can survive a node failure or a network failure. And it's just worth noting that this is all happening in the millisecond space, or even less. It's just a matter of how you're configuring your timeouts.
Okay, so this is the end of the second stage. So this is what our system looks like now. So we have a cluster of services, and now we are able to have this service being fault tolerant. And also, we are able to replicate consistently the state between all those nodes. So what is really important to understand is that the client are talking to the leader, but each model is exactly in the same state and is evolving exactly in the same state at each stage. So if we go back to the credit logic I was talking about before, with the cluster, it becomes a completely trivial operation. Because the leader knows that it has exactly the same state as the other node, as the followers, it's just able to perform directly the credit operation. We don't have to do this dance with the database or to synchronize through another system. So at this stage of the architecture, we still add some painful aspect in the architecture. So the pain point there was that we were still using a database as the golden source for our data. So how this system would work, we would have a database with all the reference data we need, and when we start the cluster, we would use a persistent service sitting on top to basically be publishing messages to the cluster to populate its initial state. The problem you have when you do that is that basically now you end up to have to manage kind of the same state within your database and also in your cluster. And we had operations like an administration UI, which was able to send commands to the persistent service, and for instance, to add a new product to the platform, and that would have to save this state into the database and also into the cluster. And because those systems are not consistent, this is quite tricky operations to do. So we are going to see how in phase 3, we are able to achieve durability. So basically being able to recover the system, the state of our system on its own. The cluster is able to do that on its own. So basically we'll end up with an architecture like that, where we don't need anymore a persistence layer and a database. And James is going to talk about that.
So before, what we were doing, when a service would start up, it would start up with an empty log. And the first thing it would do is request out to the persistent service to say, right, rehydrate me, give me all the state I need. So it would need to do that before it could do anything else. So now we're achieving durability through the log instead. So we can't do that anymore. We need to kind of have a replay strategy. So given a system in the current state, it's processed up to kind of command 4, and it's got a state where account A has a balance of $100, account B has $300. So we stop the service. So at that stage, all we've got left is the log, and when we want to start the service again, we start from an empty state. And what we have to do is this is typical in the event sourcing world. This is just a read model. Effectively, we read through the log to get the service back into the same state as it was before. So because we got the deterministic logic, we can guarantee that we're in the same state as we were as long as we replay the log in the same way. So once you start having to kind of replay the log, and you're dealing with 1 million transactions a second, say, the size of the log really impacts your recovery time of that service. So it's not typically a problem if you're not doing too many messages a second, or you can restart the model and you can start from scratch. So in order to reduce the recovery time in these kind of situations, we need some kind of log compaction mechanism. And the best way we found in the kind of models we're dealing with is snapshotting. So just to give you a quick overview of what's happening here, we've got a service in the same state as it was before. The first thing we do is we would snapshot the state. So this is kind of an operation where we take the model that's in memory, we serialize it in some form. You can do that however you choose. And most importantly, along with that information, we store kind of what position we were in the log. So at that stage, if the service goes down, what we've got is first of all, we can then continue to process commands, and the service can update the state into kind of subsequent commands. So if we lose the service at that point, what we've got is the log in position 5 and the snapshot from position 4. So when we start up the service in its initial state, we are loading the snapshot into memory first. So that gets it back into state 4. Then we just replay from that position in the log. So we don't have to replay the whole log. We just start again at position 5. So what this allows us to do is to basically archive the log up to the position where we have snapshots, and it makes the recovery time a more bounded problem.
Yes, so this is what we achieve in our third project. So at this stage, basically, we have a service which is clustered, and it's able to manage its state on its own. So we don't have to store our state in a separate database. We can just durably manage its state just with a cluster. There, I've put a database because typically in your system, you are going to have to generate some events. So in a trading system, typically, you're going to generate trades. Those trades, you don't want to keep them in memory forever. You are going to want to write them, to replicate them to another system, so you don't have some state which grows unbounded in your model. So what you would do there is basically write the trade reliably to just a SQL database in an append-only fashion, or to some form of event store. So to review what the overall architecture of the system look like. So I will reiterate. So we have this at the top level, this very cleanly separated model, which is stateful. And below that sits all the complex technical infrastructure, with all the stuff dealing with all the network I/O, all the concurrency aspects, the persistence of the logs, the persistence of the snapshots, and the replication to followers. And the good thing now is that there are open source solutions which basically provide out of the box all the technical infrastructure. So instead of building the full stack yourself, you can already find those kind of application servers and develop on top your business logic. So here are two implementations we've been using. So Copycat is a Java-based implementation of the Raft consensus algorithm. So basically, it gives you pretty much the full technical stack we have described before. it works for use case where you don't have a crazy requirement in terms of throughput. So typically in the region of thousands of messages per second. When you are dealing with something more intense, where you're going in the hundreds of thousands of messages per second or more, there is an open source project called Heron. So it's an ultra-low latency messaging system, which is being developed by Martin Thompson. So we talked about Martin Thompson before. He was the CTO of LMAX, so he knows very well this architecture. And on his left, we have Todd Montgomery. So Todd Montgomery has also been talking at YOW several times. He was the CTO of a company called 29 West, which was building a low latency messaging solution, which is used pretty much everywhere in finance, so in bank, exchange, all over the place. So together, they are building Heron. Heron is a low latency messaging solution, and which is evolving toward this application server we were talking about. So we've been talking a lot about financial use case, but I hope that you see that what we have been describing here, like this technical infrastructure, this application server, has absolutely nothing to do with finance. If you have to build reactive services, you should think about that, and you should look at this architecture. So I'll just put a few examples there of other use cases where this could work. So for instance, online games. So when you have multiple players playing together, so let's say they're playing Quake, we have a dozen of players connected to a server. The server, at any point in time, needs to have a representation of the current state of the world, so it needs to know where players are positioned, where missiles are being fired, and in which direction. If at some point a player performs an action, that sends a command to the backend. The backend is going to apply that command to the in-memory state, and it's going to produce events which are propagated down to all the players so they can update their local model. So all those online games, like gambling, if you're implementing a platform to do poker, you can use this style of architecture. And worth noting that typically in those scenarios, you don't need to be clustering your services. If your server fails over, game over, the guys connect on another server and they play their next game. Ticketing system, so that's, for instance, what is typically happening when they open tickets for the Super Bowl. Everybody goes on the website at the same time and everything falls over. Those systems, like LMAX, were dealing with millions of transactions per second. So when you have a use case where there is a lot of contention like that, those systems are extremely strong at managing with those highly contended writes on the system. And an obvious use case is basically if you are implementing a consistent replicated database or a consistent distributed cache, this is the typical infrastructure you can look at. And you can make your database and your cache push-based instead of being just request-response. And I think there are many, many more use cases that you could think of with this architecture. So I hope we have managed to demonstrate the simplicity of the approach. When I say simplicity, it's really at the model level. For you, it's a great environment to build your model. All the complexity is happening under the hood within this application server. And the great thing is that you don't have to build it yourself. So I think this architecture really requires a lot more attention than it has had in the past few years. So you can learn more about the architecture. So Martin Fowler has been publishing on his wiki a long blog post, a long article that he put together with Dave. You have also the Raft paper and the website where you can learn about Raft. They have lots of visual examples showing you what happens when a server dies, if you lose a message, so you can really understand how that is working. The guys working at LinkedIn and then at Confluent on Kafka, they are all about log. They are publishing lots of interesting articles about building log-based systems, and it's very relevant here. And finally, we've published a white paper which is available on our website and talking some detail about this architecture and the benefit of the architecture. Thank you very much.